Welcome to Wednesday morning physics with an unorganized university student. This week's quote of the week goes to Wernher von Braun, who said, "It will free man from the remaining chains, the chains of gravity which still tie him to this planet." The aim of this experiment was to build a bottle rocket from the equipment given. These items were duct tape, cardboard, string, 3 1.5-liter bottles, and other objects found nearby, including water and rocks. We first pleaded with Siri to impart her vast wisdom. She defined a rocket as being a cylindrical projectile that can be propelled to a great height or distance by the combustion of its contents. Furthermore, we decided to define requirements of a rocket. We concluded 3 things. A rocket must have an energy source to take off. It must be stable and remain so during liftoff and when undergoing displacement. It also must be designed to reach its maximum height. By observing NASA rockets, we recognize that rockets have a thruster, a cone-shaped tip, a frame or body, detachable objects, and fins. Initially, we struggled. We cut 2 bottles in half and duct taped them together. However, this design could not withstand the pressure from the gas molecules and thus failed to launch. The consequential design remained the same, except we used only 1 bottle in our second attempt. Our design methods were based on NASA rockets, which meant that we opted to imitate rather than innovate. Reasons behind our methods are: reducing air resistance will mean less contact with surrounding molecules, in turn increasing the maximum height reached. A cone-shaped nose will achieve this. Fins provide stability and direction of the rocket. We decided more was better, and so built and distributed 5 angled fins around the bottle. We filled the bottle with approximately 40% water and set the PSI to 65. We only launched once and therefore could not determine if this was an optimal ratio. We were then curious about the physics behind how a rocket works. We started with the thrusters. The fuel source of the rocket is water. However, the energy source of the rocket is a pressurized gas molecules. Once the rocket was launched, the pressurized gas molecules applies an immense amount of force onto the water. In turn, the water rushes out of the only opening in the bottom. Following Newton's third law, the downward action generated from the water causes an equal and opposite reaction, which is an upward motion of the rocket. Next, let's consider the forces present, these being a downward force of gravity, an upward force of thrust, the force of the wind, and therefore the force of the lift. As measuring the height was simple trigonometry, I applied the formulas shown in the photo, calculating the maximum height to be approximately 20 meters. However, there are multiple areas of uncertainty in the measurement. Starting with the app, from testing it on a measured 30-meter field, it had an inaccuracy of 2 meters. Secondly, the recording was done on a basic phone, so the frames per second was extremely poor, and thus an accurate measurement of its maximum height was difficult to determine. As the angles were deduced by myself, a human, by default it is plagued by uncertainty. I estimate the angle to be roughly 1 degree or 2 degrees off. Although not technically a fail, as other rockets reached a height of 40 plus meters, I deem it to be one. It provides evidence that our design was not optimal, and I've concluded several reasons why this might be the case. Firstly, when the rocket was launched, it weighed heavily and did not rotate as planned. I believe this is due to our fins being too numerous. This would have an increase in the drag of the rocket, also resulting in the force of the wind to have a negative impact as opposed to a positive rotational impact as planned. Secondly, excluding the mass of the water, the weight of the rocket was incredibly light. Using some small rocks taped underneath the cone would have increased the stability of the rocket and in turn made it less likely to sway during the launch. Thirdly, upon further research, the cone shape was way too pointed. A hunched semicircle, like used in NASA rockets, would have a decreased amount of wind from the sides, whilst providing a similar aerodynamic effect of the pointed cone shaped. In conclusion, our final design clearly was not optimal. There were many aspects which could be improved upon to increase the maximum height our rocket reaches, these being increasing the mass slightly, changing the cone shape, and using more aerodynamic fins. Due to uncertainty, I estimate our rocket reached a height within the boundaries of 18 to 22 meters. By making little alterations, I believe our rocket would have reached a much higher height.